Welcome, Calculus AB. This is section 4.2, area. The essential question is, why do we approximate area under a curve with rectangles? Let's begin. So first thing, we got to go back to something called sigma notation. I don't know if you remember this, but it looks like this big E thing, or the sigma sign in Greek terms. And this is, sometimes you might have heard it as summation notation too. It's the sum of a bunch of terms. So it's a way just to add a bunch of terms together. And it looks like this. You have, basically you're going from the lower number, I equals 1 to n, whatever n is, and you have some function here, and then you just keep doing all the terms. Let's do some examples. I think that illustrates it. So if I said the sum of I from I equals 1 to 6, basically just plug in 1 the first time, then plus 2, plus 3, plus 4, plus 5, plus 6, and you add that up, and you get whatever that comes out to, and that is about 21. So this next one, you're going I plus 1 from 0 to 1. So your first term is going to be plugging in 0. So 0 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2, and so on. So this is the summation notation for this. The next term, this is j squared from j equals 3 to 7. So 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. That's the idea behind this, all right? Some other properties of sigma notation. If you have a constant k, just like in everything else we've done, you can take it to the outside, so it'll be k times the summation of a sub I. Also, if you have two separate terms being added or subtracted, we can just break up those summations into a sub 1 plus b sub 1, or b sub I, just like we could before with integrals and derivatives. Alright, these formulas right there, you need to write these down. So these are going to be the ones we use. The first one, basically summations of a constant c, I squared, and I cubed. And they come out to equal these formulas here. Don't have to memorize these, but just write this down because you're going to need to reference this for the work. Alright, let's do an example of summation notation. So we're going to be converting to some of these examples, those important formulas I just showed you. So a summation of I plus 1 over n squared, going from I equals 1 to n, and we're going to plug in for all these values. Alright, so what I'm going to do is I'm going to rearrange this function. N squared is just a constant, so I'm going to take it outside, 1 over n squared, and it can be the summation from I equals 1 to n of I plus 1. But I plus 1 I can break up into two sums, so I'm going to go 1 over n, or 1 over n squared, my bad, times the sum of I equals 1 to n of I plus the sum of n I equals 1 for just 1. Alright, I'm going to go back and convert these. So I, going back to my formulas, I equals n times n plus 1 over 2. So I'm going to have 1 over n squared equals n times n plus 1 over 2. Plus, when you have a constant 1 there, it's going to be constant times n. So 1 times n will be just n. Alright, I want to clean this up a little bit. So I'm going to write this as 1 over n squared times, it's going to be n squared plus n over 2. I want to make this other term over 2, so I'm going to write this 2n, oh, not over 2, I want it over n, over 2. Yes, I do. This should be over 2, my bad. So this will be 2n. Let's just erase this instead. Clean up. You didn't see that. Plus 2n over 2. Alright, and combining a few things here, I'm going to have on the numerators, I'm going to have n squared plus 3n over 2n squared. And I can reduce every term by n, so I get n plus 3 over 2n. Cool. So that's what that comes out to for n. So that's evaluating for some n. Now if I plugged in values 10, 100, 1,000, 10,000, I'd get this table right here. All I'm doing is just plugging in for n. So when n equals 10, in this case I'd get 10 plus 3 over 2 times n, so 20, which will be 13 over 20, which if you plug that into a calculator, and I'll do right here, 13 divided by 20, you're going to need a calculator for this section. Oh, I did that wrong. 13 divided by 20. I'm going to hit the diamond to approximate, and I get 0.65, just like I got in the table. So I can evaluate different numbers for n. Alright, moving on. So in the last few sections, we're going to talk about area here. In 4.1 and 4.4, we found the area under a curve using integration, or 4 mainly. It was definite integration. I'm going backwards now because what we're doing in this section kind of explains how to approximate those curves using summation notation. Alright, so before if you had that function, we're finding the definite integral and the exact number, but we can actually approximate that because this is useful sometimes when we're doing real world stuff when I don't have a perfect formula to actually integrate, or doesn't follow my rules. So let's show you how this works. So let's take this example. I'm an integral of negative x squared plus 5 from 0 to 2, and we did this in 4.4, would have been negative x cubed over 3 plus 5x from 0 to 2. And so you'd plug in 2, you get negative 2 cubed, which would be negative 8 thirds, plus 10, and minus 0, because 0 plugged in both those would be 0. So if I want to convert that, I get negative 8 thirds plus 30 thirds, which would be 22 thirds, right? So that would be my answer for this one. Now, that's a definite integral. Sometimes I don't have a definite integral. I'm going to use rectangles to approximate that answer. So the rectangles are going to look like this. There's two ways to do this. Looking on the left, where I'm making rectangles with even widths, and one corner is going to always be touching the graph, or like this, and where the rectangles, the left corner is touching the graph, and the rectangles have even width. So we're going to do right. We're going to call this right endpoints. This is right, and this is going to be left. We're going to do right endpoint first. So there's 5 rectangles right here. So the right endpoints and the right endpoints are right over here, and these intervals happen if we're going from 0. In this case, we're going from 0 to 2, just like in the last example. The endpoints happen at 2/5 I. So where I is counting out, think summation notation. 2/5, 4/5, 6/5, 8/5, 10/5, where I equals 1 through 5. And the width of each rectangle then is going to be 2/5. So using that information, I'm going to write, using the summation notation, I can write a formula to figure out the sum of all those rectangles. So every rectangle is width times height, okay? And in this case, our width was 2/5. The height of the rectangle is plugging 2i over 5 into that function f. So the function f is, it's hard to see, negative x squared plus 5. So you're plugging in, for the x, you're plugging in 2i over 5. And you're doing that when I equals 1 to 5. So if you plug that in, your f of 2i over 5 is actually going to be, since f is, again, negative x squared plus 5, f of 2i over 5 would be negative 2i over 5 squared plus 5. So that's being plugged in right here, times 2/5. Now, I got the answer right here, but you're like, how did you get that? Well, again, going back to those 4 formulas, I'm going to break this up for you. So this summation notation, I'm going to expand this right here. I'll make it the sum, and I'm just not going to write the information down to make this easier for me. It's going to be the sum of negative 4i squared over 25 plus 2, because those 5s are going to cancel out here. Well, for this example. Actually, I can't do that yet. Getting ahead of myself. Plus 5. All that's going to be times 2/5. Now we're going to distribute that 2/5 in. So if you distribute the 2/5 in, it's going to be the sum of negative 8 over 125 I squared plus 2, because that'll cancel out. Sweet. Now I'm going to break this up again in 2 different summations, and I'm going to move constants on the outside. So I have negative 8 over 125 times the sum of I squared plus, well, just the sum of 2. Now you can use this and this, were both those, we had formulas for that. If I'm going back to the sheets, and I'm going to go way back because I didn't write it down either. It was I squared. So I squared is n times n plus 1 times 2n plus 1 over 6. Okay, n times n plus 1 times 2n plus 1 over 6. And don't forget times the constant right here. So times the negative 8 over 125. Plus the sum, when you have 2, it's just 2 times n, or 2n. Okay, and what's our n? Well, we actually don't have n. Our n is 5 in this case. I don't need to write n. So I'm going to rewrite that as 5 times 6 times 11 over 6 times negative 8 over 125 plus 10. And breaking up the work you saw here, use a calculator at this point. That's going to be 162 over 25, which is approximately 6 48/100. Okay, that was using the right side triangles. Let's try using the left endpoints. So if you use the left endpoints, our 5 intervals happen at 2/5 times I minus 1. So if you're going back to that graph, it's if we're starting, basically your graph's starting 1 to the right, you're going to have to subtract 1 from I every time. So I'm going to plug that into the equation, and I'm not going to show you all the work of this. We can do this in class if you want. But this breaks up, and we use those same summation notations, and you can use a calculator to find 8.08. All right. Let's say, wait, maybe you said, hey, can I actually plug into a calculator and evaluate that without doing it by hand? Yes, you can. There is a notation in here with TI-9 called summation notation. And it's under calculator's sum. And graphing calculators have this. So I'm going to type in this equation right here. Negative, and careful with parentheses, 2, we're going to call this I. I'm going to call it T instead. It's hard to find an I. Minus 2. Oops, we better get extra parentheses in here. 2t minus 2 divided by 5. And all of that is going to be squared. Yes. And then plus 5. And all that's going to be, oh, we forgot the times 2/5. So again, I can do times 2/5 at the end. I'm going to do that instead. All right. And then we're going to do this. What's the variable I have here? T. And then the lower bound is going to be 1. And the upper bound is going to be 5. And then I'm going to do times 2/5, or times 0.4. And I should get the same number. But I messed up. I think I have too many of these. Boom, there you go. 8.08. So I did it right. Again, more practice using the TI-89. I needed to. All right, we have two. So one way to call this when we have a right side, or when all the rectangles are inside, we call this inscribed, and that area of those triangles was 6.48. And circumscribed is when our triangles are basically bigger than the curve. They're all sitting outside, or the rectangles are outside the curve. And we got 8.08. So the actual area is going to be somewhere in between those two. It's bigger than this, but less than 8.08. And you know what? If you actually go back to our numbers that we did when we integrated back here, we got 22/3, which is approximately 7.33. And 7.33 is between those two. So it's a triangle. Rectangles are a way to approximate this. All right. I'm going to pause right here. We're going to have 2 videos.